Welcome back. We're going to start looking now at electrons, moving on from our protons and neutrons and looking at how the electrons are arranged in our atom and what that means for us as chemists. So there is a bit for us to know in electron configuration, and this is from our assessment guide. The first one that we're going to actually look at here is emission spectra. We'll look at that in the first video. Then we will start to look at the structure in terms of shells and subshells. And we will also look at Aufbau diagrams and the exceptions that are copper and chromium, and move through each of these different study points. I won't go through them in detail. You've got a copy of them in your guide, so we will move on. So hopefully you're all familiar with the electromagnetic spectrum, even if you haven't seen it for a while. The electromagnetic spectrum gives us a description of the energy of these different waves going from radio waves all the way up to X-rays. So this one may be in a different range arrangement than you've seen before. This diagram shows us in terms of increasing wavelength. So we can see here that as it moves from left to right, the wavelength increases. So that as the waves get bigger, our energy actually decreases. So this would be low energy light down here and high energy light up here. So you will have seen this probably as Roy Jabiv. Okay, so red, orange, yellow, green, blue, indigo, violet, and this indicates our wavelengths of light in increasing energy. Okay, so this diagram is just done the other way. So what we can see here, though, is that visible light is just a small slither of this. When we're talking about electrons and the different energies that electrons have, we actually are inhabiting this region of the electromagnetic spectrum. So transitions that we see often happen here, and then there's some that we see here and here. But it's actually the small portion of the electromagnetic spectrum that we'll be looking at. So you do need to know a little bit about wavelength and frequency, not a great deal at this point. You need to understand that the wavelength is from the peak to the next peak of your wave, or from trough to trough. Either way, but as long as it's essentially the distance of one wave. It's given the unit of meters because it is a distance. However, generally, we will be reporting them in nanometers because the wavelengths that we look at are quite small. Frequency is given the letter F and is the number of oscillations, so how many times a wave goes past a certain point in a second. So the number of waves that pass this point is called hertz, so it's given hertz as its unit. And then the energy is essentially a property of the electromagnetic radiation that these waves carry. So it depends on the frequency. So the higher the frequency, the higher the energy, and we measure energy in joules. So one of the reasons we want to look at this is because when we excite atoms, they actually give off light of a particular color. And you will have seen this when you've done flame colors before in the past flame tests, which we will do again, hopefully with a little bit more understanding of what it is we're looking at. So when we pass this light through a prism, we get a pattern, and that pattern is known as the emission spectrum. So this spectrum is unique to each atom. So the light that is passed through, so this is a gas discharge tube, it produces light from particular atoms. As the light passes through some slits and then into the prism, the light is bent out into its different wavelengths. It's bent a different amount dependent on the prism and then shone against a black background. And this is what we refer to as the emission spectrum, because it is from light that is being emitted or coming out from the substance that we're looking at. And then you can see here we have red down this lower end, then blue-green, blue-violet, and violet. In this case, you can see that they actually get closer together up at the higher energy levels, and we'll talk about that a little bit later on. But each line corresponds to a different energy level, okay, within the atom. So the light is being emitted from a different energy level. Violet is the highest and red is the lowest. There are a number of different spectra we need to know about. One is the continuous spectrum. This is what we see in A here. The continuous spectrum is the full rainbow. There's no lines of missing light or otherwise. It's just all the wavelengths of light all the way through in a continuum. A discrete line spectrum are what we see here. Both of these are discrete line spectrums. Okay, so what these means is that we see independent lines. Okay, we can see them clearly here, and they are either on the rainbow background with black lines or on their black background with colored lines. So the absorption spectrum is this one here, where certain lines have been, this is where energy is being absorbed by the substance. So this would be the light that has been shone through a substance, and it is being absorbed at these particular wavelengths here that respond to, relate to specific colors. Okay, with the emission spectrum, we see the opposite. Now we see a black background and we only see the light that is being re-emitted, and it corresponds to the light that was absorbed previously. Okay, so these are discrete line spectra, continuous spectra. Absorption is all the colors with the colors that have been absorbed missing. Emission is none of the colors and only emitting colors of a specific wavelength. So we need to be able to describe the difference between these, okay? But the line emission spectra that we see, okay, gives us evidence of discrete energy levels within an atom, because if all the electrons that are what are responsible for absorbing the energy absorb them at the same amount, then we would only get one color back. But what we see is we get different lines, different emission spectra, depending on what atom we are looking at, and these are very distinct. The same atoms always absorb and emit in the same patterns, just like a fingerprint. Okay, so the discrete or separate vertical lines, each of a different color, and it doesn't have all the possibilities for our line emission spectrum, the continuous spectrum having all of them. So this one here, the line emission spectrum, is distinct for different elements, and we will look at that. So when we think about this, if we think about Bohr's model for the atom that you should be familiar with, in that we have electron shells surrounding our nucleus of different energy. What can happen is that electrons can jump up from one energy level into another. When they do this, they can then, once they lose that energy, they come back down, and as a result, the energy is spat out, and it's spat out as light. So electrons can move from what we refer to as the ground state, so the lowest energy state, absorb energy, so they become excited, and then return back to the ground state. When they return, they emit light. So we can look at that in a energy level diagram here. N is our principal quantum number, or our shell number. So N equals 1, 2, 3, 4, 5, 6. You can see as we get higher in energy, we see convergence. They get closer together. Okay, so you can see here, this would all be emission. The lines are coming down. Okay, so the lines are actually coming down, which means that they're going from a higher energy state to a lower energy state. Along with this would come light. Okay, so light would be emitted. This is the type of spectra that we see as a result of that. So you can see that there are multiple emission lines possible because there's multiple excitation states possible for atoms. They're like fingerprints, and this is how we use light to start telling what stars are made of as well. So they're quite useful. You can see this is hydrogen. Even though hydrogen has only one electron, it has a number of different ways that it can be excited and then re-emit that energy. So we see more than one line. Okay, so that's our emission spectra. I'm going to leave it here, and we will look at what this means for the structure of our atom in the next video.